generalize this? Can we think of potential energy and kinetic energy and all the energies as part of something in a general autonomous system? Yes, but we have the problem that we actually have to build the energy function. So in general, we have the system in which we have x dot as a function of x and y dot as a function of g of x and y as well, that we call g. We assume that 0, 0 is the critical point. Obviously, it's just a shift if it's not 0, 0. And our idea is that if we find any function v of x and y that is constant along trajectories, and it has something of an interesting shape around 0, 0, then we can extract information. Let's say that around 0, 0, we're either at the bottom of a bowl or at the top of a mountain, and we know that v is constant along trajectories, then you know that, well, if 0, 0 is at the bottom of the bowl and it has to be constant along trajectories, then you have trajectories that have to be closed. If you're sticking around the contour line, you go back to the same point. Can we make this a bit more precise? Because this is a bit hand-wavy. Honestly, it might stay a bit hand-wavy, but I hope you're going to get the information about it. And the first thing we're going to do are define some types of functions. We say that v, function of x and y, defined on a domain D that includes 0, 0, then v is positive definite if it's equal to 0 at the origin and positive everywhere else on our domain D. So it is the bottom of our bowl. And we say that v is positive semi-definite if v is equal to 0 at the origin and positive or equal to 0 on our domain. That means that there might be directions or points in which our v goes back to 0. If we swap positive by negative, the only thing we have to swap in this slide is the direction of the comparative signs. So if v is negative definite, then it's 0 at 0, 0 and negative everywhere else on the domain. If it's negative semi-definite, then v is equal to 0 at the origin and it's negative or equal to 0 everywhere else on the domain. Now that we possibly have v, what we're interested in knowing is how does it change along a solution. So we take the full derivative of v with respect to the system. That means the derivative over time of v, where v is considered as a function of x and x and y are considered themselves as function of t. So if you do the calculations, this thing that we're going to be calling v dot xy, assuming that x is a function of t, y is a function of t, is the partial derivative of v with respect to x times f of xt and yt plus the partial derivative of v with respect to y times g of xt yt. And if we have some information about how v changes along a solution and some information about how v is shaped, maybe we can combine this to know how the solutions are shaped. So this is the Liapunov stability theorem. If 0, 0 is a critical point, and we have a function, v that is a function of x and y, is continuous with continuous derivative, such as v is positive definite, that means it's 0 at 0 and positive everywhere else, and v dot is negative definite on a domain that includes 0, 0, then 0, 0 is asymptotically stable. Can we understand this a bit better? Well, the idea is that you have v that is bowl-shaped, and the bottom of the bowl is 0, 0, and v dot that is mountain-shaped. V dot is negative everywhere except at 0. And what v dot means is that it's telling you that if you're not at 0, 0, v needs to decrease. And then you go and look at v, and v only decreases towards 0. So wherever you are, v dot is telling you that v is decreasing along the system, and the only way to get v to be at the minimum is going at 0, 0. That means that wherever you start in the neighborhood of 0, you have to go to 0. There's no other choice. You can also switch things around. So we have v that is positive, we had v that is positive, negative, definite, and v dot that is negative, definite, but we can switch it around and require v to be negative definite and v dot to be positive definite. V dot positive definite means that v needs to increase all the time, and v that is negative definite means that it increases only towards 0. Can we use information about v and v dot to prove the opposite? That means the instability of something. Yes. Think of a similar situation as before, but instead of v having a ball that stops at 0, it actually continues further down somewhere else. Then v dot telling you that v needs to decrease will actually tell you that you have to go through 0 and keep going. So the instability theorem of Liapunov is that if 0, 0 is a critical point and v is continuous with continuous derivatives, if v is not positive definite, that means that v is negative at some point, and v dot is negative definite, then you have an asymptotically unstable point. Why? Because, well, v dot negative definite, it's telling you that v needs to decrease all the time, but v goes through 0 and keep being negative somewhere else. Well, that somewhere else is where you're trying to go with your system. To prove instability, flipping things around also would work. You could have v dot being positive definite. That means it tells you that v must increase at all times, and v that has some positive value. It's not fully negative definite, but has some positive values. Then you have to go through it. And this is again a proof of unstable critical points. If you're able to find a function v such that v dot is either positive definite or negative definite, we say that v is a Liapunov function. Obviously, there are multiple ways to find Liapunov functions. There are multiple Liapunov functions for each system. Some are more convenient than others, and we're going to try to find out how to construct these.